we want to find out what will be the heat required to convert 4 kg of water, which is at 20 degrees centigrade, to minus 2 degrees centigrade of ice. So here first we'll draw the flow diagram. So first phase will be 20 degrees centigrade water, first will get converted to 0 degrees centigrade water. Then 0 degrees centigrade water will get converted to 0 degrees centigrade ice, and then 0 degrees centigrade ice will get converted to minus 2 degrees centigrade ice. So we can say that the transformation will be in 3 phases. The first one is the sensible heat of water, because here the temperature is changing but phase is remaining the same. In the second case, the temperature is same but the phase is changing, so that is known as the latent heat of fusion. And then again, in the third case, there is change in temperature but the phase, that is ice, that is solid, it remains as it is, so it is a sensible heat of ice. So in case of the sensible heat, the phase remains the same but the temperature changes, whereas in case of the latent heat, temperature is same but there is a phase change. Let us assume certain values if they are not given in the example. So Cp of water is 4.186 kJ per kg Kelvin. Specific heat of ice is 2.09 kJ per kg degree Kelvin. Latent heat of fusion of ice is 335 kJ per kg. Then sensible heat of water is given by mCp delta T. Similarly, sensible heat of ice is also mCp delta T of ice. So we can say that the total heat abstracted to convert this 20 degrees centigrade of water into minus 2 degrees centigrade of ice will be equal to this sensible heat of water plus latent heat of fusion plus sensible heat of ice. So substituting all these particular values over here, take m common from this. So we'll get Cp of water into delta T of water plus 335 plus Cp of ice into delta T of ice. Now substitute all these values. So here change in temperature of water will be 20 minus 0. For ice, change in temperature will be 0 minus of minus 2, that is plus 2. So finally we'll get answer as 1691.6 kJ per kg. So this will be the amount of heat that is required per kg to convert 20 degrees centigrade of water into minus 2 degrees centigrade of ice. Now let us see another example. So in this particular example, we are having the heat engine. It is receiving the heat from the 2 sources as shown over here, and it is rejecting the heat to the sink, which is at 200 Kelvin. So heat supplied is 8 kJ from 800 Kelvin source, and it is 7 kJ from 700 Kelvin source, and it is rejecting the heat Q3 to the sink, which is at 200 Kelvin. Now we know that for any reversible engine, the cyclic integral of dq upon t is equal to 0. So we can say that q1 upon t1, q1 upon t1 plus q2 upon t2 minus q3 upon t3. So here heat supplied is considered as positive. So Q1 is the heat supplied, Q2 is also the heat supplied, so both these terms are positive, whereas Q3 is the heat rejected and therefore that term is taken as negative. So Q1 upon T1, so Q1 is 8 and the temperature from which it is supplied is 800 Kelvin. Similarly, Q2 is 7 kJ and the source temperature is 700 Kelvin. Similarly, heat rejected is Q3 and the sink temperature is 200 Kelvin. So we can substitute these values over here and we'll get the value of Q3 as 4 kJ. Now we know that the efficiency of any engine is given by work done divided by heat supplied, and work done is nothing but heat supplied minus heat rejected divided by heat supplied multiplied by 100. So it is nothing but 1 minus heat rejected divided by heat supplied. Now in this particular case, heat rejected is Q3 and heat supplied is Q1 plus Q2. So substituting all these values, we can say that the efficiency of this engine is 73.33%. Now suppose in this particular example, the engine is working on Carnot cycle and it is rejecting the heat. 35% of the heat absorbed from the source. So heat rejected is equal to 35% of the heat that is supplied. The sink temperature is maintained at 27 degrees centigrade, and we have to find out what will be the source temperature. So this is the heat engine. This is the heat engine which is receiving the heat from the source, and the sink is maintained at a temperature of T2. Work is obtained in the cyclic process, and that is W. So Q1 is the heat supply, Q2 is the heat rejected, and W is the work done. Now sink temperature is given as 27 degrees centigrade, so convert that value in Kelvin. Now for Carnot engine, applying the principle, it is Q1 upon T1 is equal to Q2 upon T2, where Q1 is the heat supplied, T1 is the temperature of the source from which the heat is supplied, Q2 is the heat rejected, and T2 is the temperature of the sink to which the heat is rejected. So Q1 upon T1 is equal. Now it is given in the example that 35% of the total heat that is supplied is rejected. So Q2 is nothing but 0.35 times Q1. So we can cancel out this Q1 from left hand and right hand side. So we can say that 1 upon T1 is equal to 0.35 divided by T2. Or in other words, T1 is equal to T2 upon 0.35. So that value comes out to be 857.14 Kelvin. Convert that value in centigrade also. So subtract 273 from this value, and the temperature in centigrade is 584.14.